Today we will learn in the theory of automata or the theory of computing what is the concept of languages. So first of all, every automata understands some language. We can give the instructions to the automata or the machine. Automata means machine. So we can give the instructions in some form of a language that the automata can understand. So here, if we talk about what is the alphabet, what is a language, so see, an alphabet is a set of symbols. Okay, here in the theory of automata, an alphabet is a set of symbols. So an example of an alphabet is, this is called sigma. Okay, this is called sigma, and this is a set of two symbols, that is a and b, and these symbols a and b are called the alphabets. These are the alphabets. And a language is a set of strings over an alphabet. Okay, set of strings. So all the strings that are basically composed of these alphabets will make a language. Okay, set of strings. So suppose there is a b, this is a string. a b b, this is another string. So the set of all these strings will make a language. For example, here if we talk about the set of all English words, so we can denote it with the sigma. And suppose here E is English language. Okay, so if we write a sentence, I like to swim, so that belongs to E. But if I write like swim to I, so no meaningful sentence here, so I will say it doesn't belong to E, English language. And here this is the lambda, that is denotes an empty string. Sometimes we denote this empty string like in this way. Similarly, if we see like here, what is clean star? The concept of clean star is very important. It denotes that there is no string or a set of all possible string. Okay, so this is denotes the set of all finite length of string over sigma, including lambda. Lambda is basically empty string, na? So clean star means empty string also included. But if we have sigma plus here, closure, clean closure, it is called clean closure. Okay, clean closure. So it's mean at least one symbol will be here. No possibility of this empty string. So here there will be no empty string. So this is the example of sigma star, that empty string is also there, and the length string with length 1, string length 2, strings of length 3, and so on. But in case I have sigma clean closure, so my set strings will start from this. No possibility of empty string. Okay, now this is the recursive definition of clean star. Basis is from obviously lambda, that is the empty string. So what will be the recursive step over here? That x belong to sigma star, then x of t belong to sigma star for all. This is called for all. For all t belong to sigma. So here in the closure we can say that if sigma is equal to empty, then sigma star will also have this empty string that is not equal to empty. There is an empty string here. It is an element. This is one element. Okay, so it is not equal to something empty. Then for all sigma star that belong to empty, this is a true statement. Okay, this is true. Now, if we quickly see some more language recursive definition of function length, so you can see that if this is a length function and we have lambda over here, so it is 0. The lambda has no length, na? Empty string has no length, so its length is 0. But if in the recursive step we have a of x, so its length is 1. Yes, its length is 1. Because x, length of x plus a, there is one alphabet over here. Okay, because we want to see a belong to sigma and x belong to sigma star. And this is the symbol that is used for describing the length. And here you can see in this example that if we apply the length function recursively over the hello, then how we can find the length of the string hello? First of all, on h we get 1, there is no h. Then we apply on e, so there is +2, and then llo is remaining. Then and again L, so that is becoming 3 length, and LO is here. And similarly again apply recursively calling the length function over the hello, and only O is there, and we got 4, and after that we got 5. So the length here, now this is empty, this is the basis, okay, this is the basis, and now at the end we got 5, the length of the hello. So 0 is an identity for the addition, 1 is an identity for multiplication, and lambda is an identity for concatenation of strings. Similarly, this is another example where our bases have a power 0. Okay, and we know this thing that if any string that has a power 0, so it's mean its length is nothing. So that this is lambda here. And then we call the recursive step here in this way, like w power k is equal to k minus 1, and here w. So it's mean it will be 1, okay, and there is a concatenation. So this is a mathematical rule that if we have a power 1, and if suppose we don't write, so what we will, -1 plus 1, this will be cancelled, that is equal to w power k. So in this way we can know about the recursive step a little bit more. So here this is basically x and y are the sets, and we can denote the concatenation of x and y with dot. Okay, and it is very easy how we get this is, suppose x, this is y. So first we will multiply this x with a y, x and y with a and x. So ax ay, then this b, and again we will multiply with x and y, so bx by, and then this c with x and y again, so cx cy. So this is x multiplied by y. This is also called Cartesian product, x Cartesian product y, and y Cartesian product x is also the same. The only thing is that here you have x and a, then x and b, then x and c, then y a, y b, y c. So you got this set. So in this lesson you learn that how to find the Cartesian product or the concatenation of two sets x and y. So here we can see in the languages set concatenation is associative and set concatenation is not commutative. It's mean if you have the concatenation of x and y and then you concatenated by z, you got the same result. Okay, but x y is not equal to y x. So this is just a mathematical fun. So I hope you like the video. If you have any query, any confusion, you can ask me here in the comment. Thank you.